kerasa-kerasa. Tadi ini War, gue puter ini. Tes. Masuk nggak? Anu nggak? Cek. Cek 1 2 3. Cek 1 2 3. Cek 1. Oke, selamat pagi kepada bapak-bapak dan ibu sekalian. Oke. Siapa yang jadi asistennya? Ya udah. Berarti perlu sediain laptop juga. Belum ngecek jalan juga apa enggak ya? Ya udah. Cek 1 2 3. Tes 1 2 3. Oke.
tampil nggak ya?
Satu meja jangan
Apa?
cek cek 1 2.
Kalau di pempetnya mau nunjukin harus dari laptop itu berarti ya?
Ya. Ntar
Enggak.
itu di itu aja
Oh, gue kirim yang versi ini aja. Ini gue baru bikin.
yang biasa.
Mesin San. Aku send ada yang versi landscape-nya udah aku edit. Aku send ya. Aku kirim ke, boleh minta nomornya nggak? 08. Oh, nomorku. 0818 19 7978. Tulis aja P gitu.
Cek cek 1 2. Ini di noise suppression.
Masuk.
Cek cek 1 2. Oke. Udah kasih masuk. Kita cek.
Belum di mute. Dom.
Cek cek 1 2 1 2.
Jelas jelas.
Jelas.
Jelas banget.
Cek 1 2 3 1 2 1 2 3. Cek cek.
Wait kan sekarang. Kayak mau libat kan nanti.
Oke.
Yang mau biasa kan kalau
Cer.
awal-awal.
Oke, itu yang at existing. Oke. Oke.
Oh, jelek.
Ah. Ya dia emang kayak gitu. Nggak apa-apa. Ntar kita pending aja. Pending aja ikutin si Wesley.
Kata bapak gue kita disuruh foto bareng.
Boleh boleh.
Nanti buat katanya ini salah satu living apa living legend ini. Katanya banyak kan.
Oke, aman lah ini.
Itu foto-foto.
Iya. Udah tuh.
Ibu udah berhenti.
Cek 1 2 1 2 3 1 2. Iya. Nih, lihat ini SB-nya.
Oh,
Cek 1 2. Cek 1 2 3 1 2 3.
Bapak Ibu yang terhormat, dipersilahkan untuk mengambil snack di belakang sana. Kita akan mulai acaranya sebentar lagi jam 9 tepat ya. Terima kasih.
Cek, 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 cek. Cek, 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 cek.
Sorry, Professor, can I
Sure.
touch at your belt maybe? Maybe you can try speak.
Yeah, trial, how does that sound now?
Okay? Kurang. Oh. Maybe I will move. Okay.
How does that sound? Good?
It's good.
Good? Perfect.
Kurang.
Oh, I think I might just come down there and wait till I pull up here. Oh, no,
Start. Maybe just move it here. Okay.
Yes. There's a copy somewhere. Yeah, you can just distribute them. Yeah. Yeah, perfect. Well done.
Good morning, ladies and gentlemen. How are you today? Good morning, Dr. Wesley. Good morning, Professor Wijoyo. Thanks for coming here today. Today we are very lucky to have Dr. Wesley here. He has come very far from New Zealand, and he will give some experience about his work in Indonesia particularly. And for me personally, I met first time with Dr. Wesley maybe around 15 years ago during his visit to ITB, to Bandung. Yeah, he gave some guest lecture and about the residual soils in Indonesia. So today we are very lucky to get him another lecture, about his visit in Indonesia during his work in or maybe around 1960, 1970. Yeah. Okay. Before we start, I would like to invite Professor Wijoyo Adi Prakoso from HATTI. Maybe Prof. Wijoyo have some opening speech. Please welcome Professor Wijoyo Adi Prakoso. Thank you.
Okay, good morning, everybody. And first of all, thank you very much, Professor Wesley, for coming to Indonesia again. Although it is part of your personal visit, you still have the time to give a lecture for us. And for those who don't really know Professor Wesley, he has published very important papers on residual soils of Indonesia. As you may read in the list, there are, I think, papers from 50 years ago about Java red soils, and those are very important papers that we still refer to these days. I think those are very important to us here in Indonesia. So Professor Wesley is a very important person in Indonesia back then, the 70s, and that's why we're really grateful that you are able to give us some, well, probably more like advice for us, for the younger generations, especially for the students who are still learning about geotechnical engineering, about soil mechanics. So you could not only give us the technical issues, but I think the more important one is about the wisdom that you have come to understand, the essence of geotechnical engineering, about soil mechanics. I think that is also important in our field, and we really hope that you could enlighten us with your views, your insights after this years, and we thank you very much for coming to give us some lecture, and hope that the younger generations could also learn from Professor Wesley, and then let's start the lecture then. Thank you very much.
Thank you very much, Professor Wijoyo Adi Prakoso, for the opening speech. And before we start, we would like to invite Professor Wesley, Professor Wijoyo Adi Prakoso, and all participants to take a picture first, because we are still in the morning and the face still look fresh. Okay. Yeah. Please, we can come forward. Maybe inside the room, because we have a very good spot there. Yes. Yeah.
Underneath the sign.
Yeah. Okay, please, Professor Wesley. Okay, maybe all participants can follow the committee. Mari silakan Bapak Ibu, kita foto bersama dulu.
Sitting there.
Tuan rumah juga duduk lah. Tuan rumah lah, ayo dong buka. Okay, thank you very much.
That's good. Straight up.
Okay. Yeah, before we start, please make sure that you have snacks and coffee or drinks because we won't have any break. Okay. And now we'll be going to the technical lecture. Please kindly introduce Professor Wesley for the brief curriculum vitae. Dr. Laurie Wesley, or as we known as Dr. Laurie Wesley, he earned his Bachelor of Engineering with first-class honors from the University of Auckland in New Zealand. He completed his PhD at Imperial College London, and he had been working with Professor Alan Bishop. And he came back and serving in the University of Auckland for almost 20 years as a lecturer. And he also served in Ministry of Works of New Zealand and as a consultant in Tolkien and Taylor in Auckland. His expertise and interest includes of many aspects, but particularly residual soils, volcanic soils, tropical soils, cone penetration testings, soil mechanics, and slope stability. He also published many papers for journals and books. Yeah. And now we are gathering here in this room. We would like to see there are consultants, contractors, and even college students. Yeah, they are all interested to hear the experience, your experience during your stay in Indonesia. So the time and place is yours, Professor Wesley. Thank you.
Thank you. Is that coming through all right? How's the sound down the back?
Suara terdengar? Okay.
Right. Let me first say it is a real pleasure to be back in Indonesia and to be in this particular situation. Those who don't know my history, I should explain that I first came to Indonesia in 1960 and worked for the Public Works Department, really, from 1960 till about 1963. Then I went home again. Now I think I'll move these on, and we can have a look at the first things. It tells you something about my early time in Indonesia. Yeah, so I got the boat from Auckland to Sydney, picked up my visa in Sydney from the Indonesian consulate there, and then from there I travelled from an Italian ship from Sydney to Jakarta. And I can still remember my excitement when I woke up on the morning of arrival and I went up on the deck, and it was very hot and lots of little boats all around, lots of people on the little boats. They were trying to sell souvenirs to the people on the boat. So it was quite an exciting experience, right? So I won't spend any more time there. I came here under a volunteer scheme under which our fares from New Zealand to Indonesia were paid for by the New Zealand government. Once we arrived in Indonesia, we became pegawai negeri. With the same, that was part of the scheme. We were to live the same, eat the same food, speak the same language as the people we were working with. So that was the basis of the volunteer scheme under which I arrived here. Okay, next. That was where I first worked. It was called the Balai Penyelidikan Tanah dan Jalan, part of the Department of Pejoranan dan Tenaga. And as I've said there, I was a pegawai negeri under the New Zealand-Indonesia Volunteer Graduate Scheme. That building I don't think is there anymore, but that building was in the grounds of ITB. And that was the, you may wonder why it gets the letters BPTD. It's because that was Ejaan Lama, yeah. That the J sound was produced with a D and a J. Right. And alongside the Balai Penyelidikan Tanah, there was a Balai Penyelidikan Air. And interesting enough, the head of that laboratory was actually an Indonesian woman. I think she had trained in Holland, but it was a pleasant surprise to find a woman already in that rank over there. Okay, let's move on to the next one. The main role of the Institute was, as you probably know, site investigations for building projects. The main device used for such investigations was known as the Dutch deep sounding apparatus to the Dutch who invented it, alat sondeer to Indonesians. It was interesting enough, at that time, it was only used in Holland, Indonesia, and Belgium. In due course, it was used worldwide as what we know it now, the CPT cone penetrometer test. I could very quickly realize that it was an ideal device for Indonesia because it was very portable, well suited to the clays of Indonesia, especially the deep soft marine clays, but also to the residual clays. The Institute, when I arrived, owned 10 two-ton devices, and 2 10-ton devices, all mechanical and manufactured locally. Apart from the board and gauges, they had to be imported. With some difficulty, I changed some of the laboratory procedures, especially the odometer tests. It was rather interesting that the Dutch were very particular about the way they did their tests. And for an odometer test, instead of leaving it on for overnight, they would leave it on until the Penrhynn, the settlement, became smaller than a particular figure, which meant sometimes their tests went on for several weeks. So I, with much difficulty, persuaded the technicians that, or my boss, that it didn't need to go on that far. Overnight was ample, really, for most soils. Righto. Yeah, that's just a couple of examples. I spent a lot of time trying to learn Indonesian so I could communicate with my technicians and the technical staff. So that one was for the planned bridge over the Musi River in Palembang, South Central Sumatra. The other one is for water sections at Mount Mary. That's on the island of Flores, isn't it? I went by a plane. I'm just trying to get this flight. Yeah, I flew to Bali and then I took another flight from there to Mount Mary. It was by an airline called Zamrud, and they were DC-3 aircraft. But not long after we left Bali, one got broken down and we landed at Sumbawa Besar, and we spent the night there. Anyhow, I'll make the story short. I got on the plane at Mount Mary, at Sumbawa Besar, expecting to be dropped off at Mount Mary, but the pilot had the different instructions and he went on from Mount Mary, I think, to Kupang, and then did it anyway. The long and the short of it was, it took a long time for me to get to Mount Mary and a long time to get back home again. Okay, let's have a look now. That was one of my earliest jobs, actually. I went to East Java to have a look at a bridge collapse that you can see in the picture there. Now, it seems a fairly rudimentary, a fairly simple piece of information. This was a bridge to be over a canal. So they put the piles in before they built the canal. So they built it all on dry land. And the bearing capacity of the piles was from skin friction. So that component of skin friction, when they dug the canal, was lost, you see, so it was not surprising that it collapsed. I'm not sure what they did, I just had to report on it, and it was quite an interesting journey because my boss, I came up here as a bachelor and I went home about 18 months later to marry my wife, and my boss said, oh, you can take your wife with you. She will learn a little bit about the culture and the country. So Barbara came with me on that expedition, just to put you in the picture of what Indonesia was like in those days. When we came back from East Java, and as we were approaching the hills of the road that took you up to Bandung, my driver was getting very agitated because it was raining heavily and it was getting dark. And in those days, there were still Gorombolans operating in West Java. They were almost defeated, but my driver had a mate. They were really quite scared, but in due course, we came to the rain eased off, and we came to a little warung, and they breathed a sigh of relief, and we stopped and had coffee at the warung and then carried on to Bandung. Okay, let's have another, next one. Yeah, this was one of my first jobs. Indonesia was getting assistance from Russia to build that new sports complex for the Asian Games. And I used to go down, they were using our technicians to do field testing, And I used to go down about every 2 weeks partly to be a translator. The Russians had 2 translators. They could translate very well from Russian to English, but they couldn't translate from English to Indonesian. So my job was to come down, and I was always given a very warm welcome by the Russians because they couldn't communicate with my technicians unless I was there. So we got together and we went out to where the connections was, and I had to listen to the Russian engineers speaking Russian, and then the translator would translate that into English, and I would translate it into Indonesian for my technicians. So it was a fairly slow process. And that's the finished stadium on the right-hand side there. I used to stay sometimes when I came to Jakarta with a friend in Kebayoran, not far away from that. And on a Sunday, I used to go for a run down to the stadium along with all the other people on a Sunday morning going around it. And I would like to have gone into it, but the gates were always closed. But one particular day, somebody said to me, go around the other side to the gate. So I went around to the other side and explained that I wanted to go in. And the man said, okay, sebentar saja, he said. So I went in, and it was being used by various athletic groups. They were in various places. And I thought sebentar saja is not particularly exact, but it would give me sufficient time to run one lap of the stadium. So I do a bit of running. So I run around, and as I came back, a gentleman in an official uniform came up to me. I don't know how he knew I knew Indonesian, and he spoke to me that you're not allowed in here. You have to be in one of the groups, and you shouldn't be here at all. So in my best Indonesian, I explained to him that about 50 years ago, I was involved with the planning and the building of the foundations of the stadium. And he listened very carefully, and then I apologized again and said, I must get out of here. And he said, oh, no, Tuan, boleh satu lagi, dua saja kalau mewakili. I could do one more lap or 2 more laps. It was not just what Indonesia is like, actually, that he had a very official position, which he thought he'd better make sure that he was obeying the rules. But in the end, all right. Next one. During my time in Indonesia, I went to Ambon to check site investigation work being done by BPTD to enlarge the Indonesian naval base there. That was being done with aid from Russia. The Indonesian Navy was receiving aid from Russia for this, and an officer of the Navy came to Bandung to engage the Institute to carry out CPT testing and drill boreholes. My trip to Ambon, it went off semi-smoothly, except when I got off the Hercules in Ambon, I heard the person meeting me say to the pilot of the plane to say to him, when this plane takes off, that will be the last flight from Ambon for some time. And so I listened a bit surprised, to say the least, because then I said, but I've only come here for one day, and then I want to get a flight back. They said, oh, well, you can't. And I said, so how can I get back to Bandung? And they said, oh, you can get a boat to Makassar. So I said, is there an agent here? Oh, yes. So I went to the agent. Fortunately, there was a boat back in about 2 days' time. So I got the boat to Makassar, and eventually from Makassar, I got a Garuda flight to Jakarta. I was worried, you see, because my wife was pregnant and expecting our first child. And I met there was an American there supervising the construction of a wharf, and I met him by chance a couple of months later in Jakarta. He told me I was very lucky because he had to wait another 6 weeks for the next flight out. Anyhow, that's a little bit about. Now, my trip to Ambon was interested to the intelligence spy unit of the Australian Armed Forces. When my term came to an end, I flew back to New Zealand via Sydney because I had relatives in Sydney, and I stayed overnight there. Just as I was almost dressed the following morning, my aunt came to me and said, are you dressed? And I said, yes. She said, there's a gentleman at the door wants to talk to you. So I said, I don't know anybody here. So I went to the door. He introduced himself as a member of the intelligence unit of the Australian Armed Forces, and their job was to find as much information as they could about anything of interest to Australia. So I don't know how, again it shows you how the intelligence systems work. I don't know how they knew that I was staying with my aunt in Sydney. So I chatted them for a while. They asked me if I had any photographs. I did have a box of photographs, so I gave it to him, and he picked out the ones to take a copy of, brought it back to me the following day. So to this day, I will never know how the Australian intelligence knew that I had been to Ambon and I was calling there on my own. Okay, come on to something more serious. I went back to Auckland after the appointed time, about nearly 3 years, but I came back to Indonesia to the same job at the Bandung Institute as I had the first time, but no longer as a pegawai negeri. I was paid by the New Zealand government that time. I stayed there till 1979. I had some rough ideas of what I intended to do, in particular the following: to teach and train the engineers and technicians in the institute and in the public works department. That was one thing. The other one was to get a better understanding of Indonesian soil conditions, learn a bit more about Indonesian customs and beliefs, because the first time I was there, we were very busy. I spent all my time supervising, not really engineers, but last year, students, I think, writing reports and things like that. Okay, let's have a look at the next one. Yeah, I made teaching and mentoring an important part of my job. So the public works department, or let's say the Indonesian government, they wanted to set up much better laboratories around the provinces, and they wanted to send engineers and technicians to Bandung for, I think, 2 weeks to do a course in laboratory testing and things like that. So I put together a set of notes and things to give out to them, and I did that demonstrating myself. So on the left you can see somewhat younger me teaching them how to do Atterberg limits, and on the right, yeah, similarly, somewhat younger also, explaining the triaxial testing. That was Ibu Sulastri. She was in charge of the laboratory, and sitting down on the right-hand side, her name was Hardani, and she became very expert on triaxial testing. And the aftermath of this was that an Indonesian structural engineer saw the notes which I had prepared for teaching, and he said to me, Laurie, you should put those notes together and complete them so they could be published as a textbook, which was something I had never thought of, but I did do that. And if you look at the bottom, that's the sequence of books that came about. That very one at the left, people who are my age will know what a Gestetner machine is. Do you know what a Gestetner machine is? Almost nobody here of my age. You had special typing systems that produced little cuts. Then you put it into a wheel, and you turn the handle, you see, like that, and it printed them off one after another, and then you put them together. So that one there is a copy, I photographed it, of the first, that was so tedious it was in 2 volumes. That's Babak 1, isn't it? And there was Babak 2. But it sold so rapidly that the Badan Penerbit from DPUT had a very clever guy, his name was Saroso, I think. He reformatted it into the 1975 version. They used to call it the Buku Yang Chocolate Itu. And it kept getting printed, I think, until about 1999, when a new government came into power who liked to privatize things, something like that. Anyhow, they closed down the publishing unit of the Indonesian Public Works Department. And then I kept getting asked each time I came here, when was I going to produce a new edition of Mechanica Tana? And I always said, when I retire. So when I retired, I set out to do it. But I thought maybe I should write a more comprehensive book for all of the English world, and then I could translate it into Indonesian for an Indonesian version. So I did that and sent my proposal to John Wiley and Sons, probably the best known company in America publishing soil mechanics books. So they accepted my proposal and gave me a contract. And so that got published in 2010. And at that same time, I was teaching in the University of Chile, Chile in Santiago. And they wanted me to teach a course in residual soils, really. So that's why there's a second book there called Geotechnical Engineering in Residual Soils. And then I set to get it only the first one, not the second one there. Only the first one I translated into Indonesian. And then that came out, as you can see on the right-hand side there, 2013. And then I was told, and I knew, it had too much advanced material to be suitable for an undergraduate course. I was really trying to do 2 things: to produce a book that would be good for practicing engineers, not just students. So that's why it was regarded by my colleagues at various universities that was a bit too much in it for students. And why didn't I write a new version of the original Mechanica Tana? So that's why I did that, and you can see that got published in 2017. And that company in Yogyakarta, Penerbit Andi, isn't it? Andi Publisher, does a very good book, a very good job of publishing books. They're excellent. Okay, let's see where we can get to some practical things. Yeah, if you travel from Jakarta to Puncak, which I used to do quite regularly, I noticed that when you got to a certain limit, the red colour disappeared, and it came a sort of a yellowish grey colour above that particular limit, and it was about 1,000 metres above sea level. So I was a bit intrigued or interested in finding out what was going on here, that you produced a red colour and a much lesser colour up there. The simplest answer is, of course, that the weathering is much more intense when you have a higher temperature. So you've got a higher temperature in the Jakarta area, getting rid of a lot of your silicas and leaving behind I'm not sure, I can't think of the name, but it leaves behind the elements that give it the red colour. Obviously there are elements that give it that red colour. And then I started to look for how could I find out a bit more about this. Yeah, there were 2 people who were very helpful to me. One was for geology. He's died now, but his name was Mulyono Purba Hadiwijoyo, and he was at the Pusat Geology in Bandung. The other one He was in the Pusat Penelitian Tanah in Bogor. That was a institute for doing research for agricultural reasons, not for technical reasons. But they were very trained by the Dutch, and they gave me a copy of that map that you see there, and that boundary there between the white and the other, that's about the 1,000 meters, you see, so it tallied and explained a lot about what they told me the minerals for the high altitude was that the main clay mineral was olefin. Down closer to Jakarta or down lower, it was mainly a clay mineral called halloysite, and they have very particular properties, extraordinarily different properties. Okay, the remarkable properties of clays derived from andesitic ash. Those are the most photographed rice fields in Indonesia, I think, because every tour bus in Bali stops so people can take a picture like that. So I took a picture like that. But if that was the sort of soil that we are used to in the West, or particularly in England, there was no way you could build rice fields in England or in Europe. It would collapse. And it's not only steep, but it is also full of water. You see right along the top there, you can see the canal that's bringing in the water for the rice field. And the water flows all the way down, so it's fully saturated all the time. That still remains stable. Next. Yeah, there is a limit to how steeply you can cut in it, but that is all olefin clay there, with water contents about 160 or something like that. Amazing material, but you can see there is a limit, that they had a slip there, and I was sent down to solve the problem. If you've got something or other, a white skin, you can solve all sorts of problems. Anyhow, I went down there. One of the strange things they did was to build a road wide enough for vehicles to pass. That was absurd. They should have chosen the places where it was not so steep to give them the passing bays. But I told them, really, you're just going to have to wait, and there will be more probably be some more, but not too many, and you'll just have to remove the stuff and it will settle down eventually. It was to a transmitter station somewhere up at the top of, I've forgotten the name. It was in Central Java, not too far from Sumoto. Okay. Yeah, now this is interesting. This is Cipanunjang Dam near Peng. It should be PENG, shouldn't it? Pengalingan, for the Bund water supply. It was built by Dutch engineers in the late 1920s. It's about 30 meters high, consisting of olefin clay. Not that the Dutch engineers knew it was olefin clay, but there was various Dutch magazines, technical magazines, which have accounts of building this one, and somebody gave me the English translation of them. And the interesting thing was that the Dutch had planned 2 dams for water supply. One was this one here. The other one was down on the flat where the soil was totally different. And the one that was down below, which was built of a normal clay, as we talk, it failed before they reached that size, and I think it was abandoned. Whereas this one, you see, has been used right through, and it's perfectly stable. And they are world leaders, the Dutch were, in the construction of water retaining structures. And they've got piezometers, vertical tubes, and they take measurements and they've got internal drains picking up the seepage and concentrating it in the little round structure you can see on the right-hand side there. I've been to this dam several times to show people, but I think the first time I went there, I went into the little round thing there, and there was a man there. He was keeping the records. His job was to go around, drop his weight down to the bottom of the piezometers, and then record the depth, the stuff. And I said to him, and then what do you do with the records? Oh, he said, well, not very much, but sometimes an engineer comes and has a look at them. So they were very well taught by the Dutch, but they weren't so well taught or supervised afterwards. But, you know, and it has got a nice, I forget what it is, right? It's got an internal drainage layer somewhere here. It's very well built, which collects the seepage and feeds it to an outlet down here. Yeah, as I've said there, it was about 30 minutes. It's an example of elephane clay. They did have some problems with compaction, which you will often have with elephane clay, because they're very high water contents, and they are what we call sensitive. If you drive over them and things like that, you turn them into porridge or some sort of very, very soft thing. Okay, let's have a look at the next. Yeah, this is a portrayal of the difference in the clay minerals between conventional soils and the soils derived from andesitic eruptions. Hopefully you are all familiar from your basic soil mechanics of the top three. You see, those are the structures you will find for kaolinite, illite, montmorillonite. But the halloysite ones, these are nothing like being to scale. The halloysite ones are probably at least 100 times smaller than those other ones. And the ones on the right-hand side are even smaller. And the elephane consists of very, very tiny spheres, and these threads were winding their way through it. It took them a long time, actually, and in fact it was the Japanese who developed the technology to take photographs of the structure of elephane and halloysite clays. Right, next. Yeah, that's a picture on the plasticity chart. If you look at the weathered sedimentary soils, yes, so they're strung along up above that A line there, and they are generally not the sort of soils that geotechnical engineers like. They are very highly plastic, they've got low strength, they tend to shrink and they tend to swell, all the sorts of things that geotechnical engineers don't like. Down on the other side, the red triangles, those are from the red clays of the lowlands, and the blue ones are from volcanic ash. Now you can see that the liquid limits you get from the elephane are almost up to 40, and you can have water contents up to about 180 or something. One of Indonesian engineers, he owned a company that undertook a lot of soil testing and field testing. He told me that one time they were taking samples from the highland, and the water contents were all very high, and they were doing it for an American company. But when the American read his report, he told him, that's nonsense. You can't have soils with water contents like that, only as high as maybe 100, but you can't have 150. And he had to argue with him for quite a long time. I think he invited him to do the tests himself. Anyhow, that was the reaction of many people from the West, that you couldn't have soils with, especially not stable soils with water contents that high. Now, a very important point about this chart is, if they plot on the downside or the right-hand side of that A line, This was dreamt up by Casagrande as a means of classifying soils. And he would classify, quite rightly, anything below that line as silts and anything above it as clay. Now, the way Casagrande did this, you need to realize how he did it. He gathered together soils from different geological origins. So he got as many different soils as he could. Then he tested them, and he did the usual hand manipulation tests to distinguish between clay and silt. That was the basis of it. And so he looked at them, and he looked at those, and he drew the lines up, you see, from his interpretation of which ones were clay and which ones were silt. So he made that interpretation as the usual manipulated test. You know, if you want to find out whether a soil is a clay or a silt, you should get hold of it, adjust its water content until it's not sticky. It's really nice to manipulate it. Then you put it in your hand, and then you smooth it out nicely in your hand, all right? And you'll see it's got it doesn't shine. Then you vibrate it. You vibrate it quickly like this, and you, in effect, you liquefy it. So that's the property of a silt. There are other properties, which was a bit tedious. If you stick it in the oven, it'll come out rock hard if it's a clay, but if it's a silt, you can almost press it like that and it'll fall to pieces. So the basis, don't think that you can give a classification to a soil or confirm the classification by doing Atterberg limits. Your fields testing is far more reliable than what you will get from the laboratory tests. Righto. And these are compaction curves, because it's when people are doing earthworks in elephant clays that they have the most difficulties. And what I did here was something very careful and very tedious, because I had to have as many samples as are shown on there, because we didn't test the same soil twice. We used a fresh sample for each test. So if you have a look at the top one, as we dried back along here, the material was becoming more compact, and eventually we came to a point where we could put it in the oven and dry it. If you put a soil with a high allophane content in the oven, it won't come out as a clay. The oven will change the properties of the allophane, so it's no longer plastic. You can't do Atterberg limits on it if it's a high allophane content. So I don't know what you do here, but I teach anybody in New Zealand not to dry the soil out before you do a compaction test. Adjust it to whatever water content you need by drying it back. Don't dry it away. The easier thing is to dry it way back, and then you just add a certain amount of water to each of your samples, and just, that's the easy way of doing it. But if it's allophane or halloysite and you dry it out, you altered its properties. So the curve at the very top of the top one there, that's after it had been in the oven. I've got a key there, haven't I? Oven dried is that little curve right up in the top there. So the material is totally changed by drying it out in the oven. Then if we came down to a certain point, a bit less, and then we wetted it up, we get another curve, you see. So what tends to happen, and I know it's happened on a number of sites in Australia and New Zealand, that the people do tests from samples coming in from PNG or somewhere, and they've got the properties of the material here. So they do a test like the air-dried one there, right, on the top graph, that air-dried graph there. They do the test, so that gives them a maximum density and an optimum water content, doesn't it? And then they write a specification based on that. But when the person doing the earthworks does the earthworks, they're not going to dry it any drier than they need in order to do it. So they will dry it back so that the water content is directly below the maximum value of the air-dried samples. And they find that they cannot reach the dry density that has been specified for it. So then there's a contractual dispute that goes on and one of those sort of things. So the main point, the main point about red clay is the tropical red clay is the ideal geotechnical engineer's material. It is very ideal. It's got high strength. It's not compressible. It doesn't shrink. It doesn't sell. And its water content is usually very close to the plastic limit, which is again very close to the optimum water content for compaction. So tropical red clay, or particularly the red clays all around Jakarta, they're ideal for earthworks. Okay, let's move on from here. Yeah, now I was interested in the shear strength properties of the red clay, and I was rather fascinated by it. If you drove from Jakarta to Bogor, for some distance, you were right alongside this quite steep bank, you see. So I had a little, I borrowed there's a little thing called an Abney level where you can measure angles and you can measure heights. I had a technician with me, and we measured a lot of these ones. And so the surface was definitely red clay, and it was a little bit different getting deep down, but as far as we were concerned, it was almost all red clay. So then I took some samples, had some triaxial tests done so we could analyse it and see if it made sense. Here, carry on again. Oh, what did I say here? Yeah, the banks were very steep, a suitable place to investigate the stability situation. This was about 1970. Yeah, okay, carry on. Next. Yeah, had some triaxial tests done. We put down 2 boreholes, but we only went a metre depth because that was all that was interested. So we established those parameters that you can see there. Okay. Oh, now you'll be expecting to see a safety phone stack, a safety factor, but I'll show you in another slide. Why not? Yep. I did calculations and I did slip circle analysis, all manual, no computers in those days to get you. And that's how it looks. You see. What I was looking at was the change depending on the pore pressure, and you will know in the Bishop method of doing slip circle analysis that he defines as a parameter RU, which will vary from quite a negative value to a positive one. So that analysis was showing that you didn't need to have very much pore pressure before your safety factor fell down to about 1. Now I'll say a little bit about personal computers. I left the Auckland consulting company, Tonkin and Taylor, moved to Auckland University in 1986 at the age of 50. This was the time when personal computers were already in use at the universities, and consulting companies were starting to make use of them. I eventually learned how to use the slope stability FlowNet programs, Slope W, Seep W. And looking at my early papers in geotechnical, I came across that early. I wrote a paper of it that went into geotechnique. But I thought I should really have another look at it with these much more upmarket means of analysing. So, as I said there, slope W and Seep W are very good. I mean, universities they're very expensive for individuals to buy, but universities could buy them quite easily. And the good thing about them is that you can start off with a particular water table, and then you can imagine the rain falling and raising the water table, and you can use the seep program to give you the seepage pattern at each stage, feed it, or you only have to push the button, and then the stability analysis will repeat it using that new flow net. So I thought I should say at the start, I'm not sure whether computers have more benefits than negative benefits, because all around the world, people are doing geotechnical engineering sitting in front of computers. And they're never going to become a good geotechnical engineer sitting in front of a computer unless you get into the laboratory, get down to the drilling rigs or the SPT things and find out how that is done. You won't be a good geo. Okay, let's keep going on. How am I doing for time? How long have I got? Say that again. 12 o'clock. I'll be finished long before then, for sure. Yeah, the computer has its place, and I mean, what I found out using slope W and seep W was they're very helpful to give you a better understanding of various phenomena and things like that. But if you think you can somehow predict the rainfall and all the other things you need in order to assess the stability of a natural slope, then that's dreamland, really. Okay, let's move on. Oh, now here's a bit of heavy. If you derive the, most of you will know the Laplace equation, which is a very simple equation. But if you do the same analysis of a segment of water and put time into it, you come up with the top one there. You've got the dimensions on the left-hand side, and you've got the time issue on the right-hand side. Now, if you don't have any time in it, then you just get rid of the one on the right-hand side, and you come down to the Laplace equation. That one there, like that. And for one-directional flow, you can get rid of one of those directions, and then you've got the normal Terzaghi consolidation equation, the second one up from the bottom. I mean, you convert Ka over MVW into the coefficient of consolidation, don't you? It's interesting that most textbooks treat the Laplace equation and the Terzaghi equation totally separately. They never link them together. But one of my friends in Ireland quite recently, he uses my book. He said he really liked the way I treated seepage and consolidation and one-dimensional flow. Yeah, let's move on from that. So I went into the, I made use of both of those programs. And to use those, I had to get some additional coefficients, but I did have some fairly reliable data. So I set about having a look at it. Carry on. Yeah, now this is how I looked at it. That's the same slope as I showed you. And I assumed that it was the end of a long dry spell, and the initial water table was pretty deep. You see, it's quite deep right at the bottom there. So I assumed that that was the initial water table. And then I assumed that it would rain and rain and rain and rain. So that immediately gives you a zero pore pressure on the ground surface. So those are your limits of the analysis. And you can, if you want to print it off, you can print it off as for each time segment. But what I've printed off there is for the last time segment. So the rain is still falling, so you can see what's going on there, that water is entering at the top, and at some points it enters at the, it goes out onto the face itself, and eventually it's established that long-term flow net. And looking up at the safety factors, when the water table was down deep there, the safety factor was 2.14. In its final state, it was below 1. So according to that analysis, the slope would fail at a certain stage or at a certain duration of rain falling on it. Okay, and there's a few other things that are quite interesting to look at other patterns. Let's just have a look at those. Yeah, this is showing the initial hydrostatic state. That was when the depth of the slope was 10 meters, wasn't it? So that initial one there was the initial hydrostatic state. A point which is of supreme importance, especially in the countries with a lot of rainfall. The textbooks, particularly when they show you cross sections of dams, they show you a flow net which has a surface well below the top, if you remember what I'm getting at. What I'm getting at is this: where you've got most clays, your water table, you cannot draw your phreatic surface going through the clay, as a lot of people do. If it is clay, water does not drain out of it under simple gravity forces. It will never drain out. The capillary effect is much too strong, so your actual water table will always be some distance below the surface. But when you see, Tertsage and Casa Grande were as guilty as anybody, because their float nets, when they are looking at embankments and things, their flow nets all go along somewhere, some distance below the surface. That would only be correct if the material was sand or gravel, but you're not going to build an embankment of sand or gravel because the water would just flow through it. So that the way that Casa Grande and Tertsage drew it, it got established in the literature. You won't find a textbook that hasn't got a flow net like that. So the only ones that they would be building for a dam would be clay, not sand or gravel. Okay, so that just shows how on a particular line, it's different how far or how out of the slope is. It just shows you how the seepage pattern is changing as the days go on. So the contours there for 0.2 of a day right through until at about 20 days you reach the steady state one there. That one will never be hydrostatic because it's a seepage situation. The theoretical hydrostatic one is further out there. And let's have another look. I think I got one showing you how the top one shows how the safety factor changes with time, and as time goes on, the water table rises and the strength goes down. So according to that, it looks like it had about 2.5 days of steady rainfall before those slopes would fail. Now, I'm not saying this is gospel truth or whatever, but it is an indication at least of the most likely situation you've got if the soil is all nice and uniform and things like that. And the one down below shows you how the water table itself rises, and it rises fairly slowly at the start, and then it rises fairly rapidly as you get up near the surface. And that's just looking at the pressure head at a particular, or at the depth of 10 near the bottom of the slope. Okay, let's move on from this. Yeah, that's just comparing my original analysis, which I did by hand, with what came out of the computer, and looking at our chart of the pore pressure against the safety factor. The manual analysis was a nice straight line. The slope W analysis was a little bit different. I haven't sat down long enough to try and figure out why that is, but what I'm saying is that the time I spent doing circles by hand, I mean, you have to do a whole lot of circles by hand before you can get the answer. It did come out pretty well. Well, I was putting a paper in geotechnique, so I had to be fairly sure that it was reasonably reliable. So I did quite a, but you get a feel for it fairly quickly after you've done one or two circles where you need to go through. So that was, for me anyway, it was very satisfactory that the computer system came out with the same as what I did so many years ago. Okay, let's have a look on that. Yeah, now this is a side issue, but it is an important one, particularly in my country. The stability of the vertical banks, especially trenches. Far too many lives have been lost because people worked in trenches that appeared perfectly safe or which analysis showed had adequate safety factors. And it should be recognised that it is not possible, either on the basis of theory or of experience, to say whether a particular trench in soil will remain stable. Just be very clear, I'm talking about a trench, not about a circular excavations. Since time immemorial have put down wells. They don't collapse because there's no sort of collapse mixing if you've got a circular well, whereas there is for a trench. A vertical bank is dangerous. Vertical banks don't last long. So if you're working alongside a vertical bank, it is dangerous, but you have some likelihood of surviving because it will fall down and it'll push you sideways. But if you are entrenched, you've got no way out. It will show that it's about to fail, and it will fail. I was in a court case once in New Zealand, and they got into a situation where they were piping and they had to go deeper than they wanted to go. And the foreman doing it, he was doing it, he knew it was in a dangerous situation and he asked his men to keep an eye on it, but it collapsed, and it collapsed far too quickly. It buried him and killed him, and the court case I went to was involved with prosecutions about that. So just be very clear that you can't go to a textbook and find out how safe your trench or your bank is going to be. Soil mechanics textbooks often give the following, well, you'll find them there if you look. For the maximum height of unsupported vertical banks, you've got one for the effective stress, another one for the undrained shear strength. And now let's have a look at what they give. Right? Here, if you look at that, the left side there, I adopted some parameters which I thought were reasonably real. And with one set of parameters, if you do a total strength analysis, you're going to be safe in a trench 24 metres deep. I mean, if you put a safety factor on it, you come out with 8 metres. Effective stress analysis is a bit more realistic, but even with a safety factor of 3, I think, it still comes out at 2.4 metres. Most authorities dealing with these sort of things, some give 1.5 metres as the safe. I would prefer to have 1.2 metres, because when you're working in a trench doing pipe work and things like that, 1.5 metres in my mind would be still risky. And interestingly enough, I just thought about how many natural slopes I'd actually seen. The bio pit for the Chipanunjang Dam that I showed you, it's quite impressive really, and it's a slope of 45 degrees and it's still stable. And it's an interesting case because above that, the ground is shaped in such a way that the water is running towards the slope. In other words, it's concentrating the water. But that's another thing about elephant clays. When you make a cutting, they resist erosion. Whereas if it's, for example, weathered granite, if you go to Malaysia and drive along some of this, the weathered granite is terribly erodible, whereas the Elephant clay hardly erodes at all. And then I looked at other ones, and I've got the 70-degree one there at 5 metres as being stable. Oh, and the next one, 10 metres at 60 degrees. That's that one that we looked at. So, let me see what else I've said here. Textbooks present the theoretical quotations without any warning that they cannot be applied in practice. John Atkinson, who's a well-known promoter of what they call critical state soil mechanics, in one of his books states that the one commonly used in design is HC equal to 3.8 SU over gamma. And he uses a strange theoretical argument for his value. But that statement is like a recipe for disaster. If you put 33.3 in there and calculate the safe depth of a trench, you're just inviting jail. So get it very clear that people should not be working alongside vertical banks. And one time there was a vertical bank on a construction site where I was, and it was a bit undercut down below, and people were working in it on a pipe. I knew where the foreman was, and I went down and I said, "You realise what's going on up there?" I said, "If that bank collapses, you'll be in dire straits." And he said, "Yeah, I'll go and have a look at it." And he got his men out of it immediately, yeah. Right, let's see what else I can talk about. Yeah, this is my interpretation, all right? I'm talking about whether conventional soil mechanics can be applied. If it's vertical, it's almost certain to fail. Theory is very wrong. If you cut it at 80 degrees, it does actually make it quite a lot safer. But you still couldn't rely on theoretical soil mechanics to tell you that it's safe. And neither would I recommend it. But then we come to the one that I've just showed you, about 70 degrees. That one, and I haven't got a very strong basis on which to say that, but on the basis of what I just showed you, conventional soil mechanics does give you a proper answer for, and in that particular case, nature itself tells you, doesn't it, all along that stream beside the road there, they were stable at that length there. But that may not apply to other types of, well, most other types of soils are not going to be at 70 degrees anyway. They're going to be a lot flatter. Okay, let's have a, yeah, this is just emphasizing how difficult it is to apply theoretical methods to estimate the stability of residual soils. That one on the left, that's weathered sandstone actually. That's a road they were doing in Malaysia that I was involved with. For some reason, their consultant had recommended slopes of, I think, 2 vertical to 1 horizontal. They were ridiculous, really. And I think even 2 horizontal to 1 vertical is still pretty steep. But the point I'm making is those ones have got discontinuities. There's no way you can predict where your discontinuities are and where they're going to fail. And the one on the bottom, that's in Papua New Guinea. And the reason they had me there was that there was a multi-billion-dollar gas field up on a higher plateau, and they were trying to get their road from low down up to the higher plateau, and it was proving difficult, as this one showed actually, that they were having some problems on that road. An interesting piece about the way big energy companies operate was they called that the tax road, and they had to do something to justify some certain figure of expenditure. I didn't ever understand it, but they called it the tax flows because it was enabling them to fill in their books and reduce tax, you see. But right at the end, when we had our last meeting with the people, I said, look, you really got to work it. The geologists were saying, oh yeah, they could do it this way and they could do it that way. I said, you've got to accept that you're not going to get away with what has been proposed. It won't work. You've got to accept the fact that you really have to spend a lot of money. And I told them how they could spend it, how they could build it. You see, they have problems with these energy companies, a lot of very heavy equipment. So they have to get it up there. So the criteria for your highway is very strict. It has to very low gradient and a very gentle curvature as well. And I said, you're going to have to do something else. They went away and costed it, and it came back as 500 million. And the boss said, well, it is an 80 billion project, so we could look at it. But after some time went through, I had a phone call when I was actually working in Chile, and it was about compaction. What advice I could give them about compaction. What had happened was they had decided it was not viable to build the roads, and the Russians had a giant plane that would raise very heavy loads. So they, instead of trying to take all of their heavy equipment up by road, they took it up by this one giant lifter that the Russians brought out for it. So that's why my friend was involved in compaction, because they were compacting a runway for the Russian to land their big plane on. Yeah. Now I'd like to show this one. This is the first geothermal project was at Kamojang. Kamojang, which is up the hill. If you go right down to the most southern part of the Bandung Plateau, it's closest by road from Garut, I think. You go to Garut and then you can go, or you can go up. I think the road has probably improved a lot now. You can get up to the site by road. Now the piece you can see at the end, that was stage one of this geothermal project that New Zealand paid all of the external costs, and Indonesia paid all of the internal costs. And they came here, two experts from New Zealand, one a geologist, one a chemist, to work with the staff of the Geological Survey to travel around Java and see where they could find the best sites to use for building a first geothermal power station. And I went, I knew the two, I went up to Kamojang with them, and they had a good look around it. And in the end, they selected Kamojang, and it was an ideal site because there were no stability problems. And what you like when you're doing investigating a geothermal field, you like to have dry gas, some gas, dry steam. You don't want a whole lot of water coming up, and neither do you want chemicals in it. You know, sometimes you have to do a lot to separate the water before the steam goes through the steam turbines. So the first one worked very successfully, and they went ahead to do the next ones. So this is, go back again. Yes, this is the second stage. And I didn't see them doing it for the first stage, but they probably did it the same way. And it is a wonderful way to do it, because a lot of the allophane clays are rather sensitive. If you put heavy machinery in it, it softens it. So here the excavation was done entirely manually, And you can see all the work that's been done there. It has all been done manually. So it doesn't disturb the natural strength of the elephant clay. And I came back to that site. No, stay back on that last one. I came back after it was, my calculation from analysing all of this before it was built was probably they would be up for about 20 or 30 millimetres of settlement, which is probably just about enough. You might find a little bit of cracking in your thing. So I explained to the guy that I was very interested in the connection, and he took me down below to have a look at it. And there was no sign of any cracks at all. So don't rely on this, but generally when you do an estimate of the settlement of a foundation on residual soils, it will generally be quite a lot less. Sort of a bit of comfort anyway. So there was wonderful seeing all this stuff done by hand, because it didn't disturb the soil. And not long after that, there was a company in New Zealand building a paper mill down there at the foot of one of our volcanoes, which produced exactly the same sort of soils. And they had heavy machinery in doing their excavation, and it was just a mess. That's why I got sent down from my company to sort it all out, because they had heavy machinery, and it was just turning it to porridge, or slush as we call it in New Zealand. So I told them, well, they'd have to get a very light track machine to go along and scrape up all of that mush. Come in from the far side with a layer at least 0.6 of a metre thick of gravel or something like that, and then you could have a decent platform to work on. And so I presume they did it anyway. Okay, let's see what else we got. Oh yeah, this was, I'm not sure. When they were about ready to commission it, Galunggung started erupting, and Galunggung was not far away actually. Those two pictures at the bottom are of Galunggung erupting, and that's Tasikmalaya that you can see there. And I did not take those photos. Somebody else took them, and hawkers in the street were selling them to anybody interested in photographs of Galunggung. It was interesting too from an aeronautical point of view, because it became a very famous case, because a British Airways plane flew into the ash cloud, and all of its engines stopped. One stopped, and then another one stopped, and another one stopped. They hoped they had to drop it down to about 13,000 feet or something, because they wouldn't have had any air to breathe or something. He dropped it down to there, and then he hoped he could glide back to Jakarta. And they almost did, but they got to a point where clearly they were not going to get back to Jakarta, so he turned it around and prepared to land it in the sea. And they have a procedure for restarting the engines, and they kept going through it, and on the 7th time, one of the engines was started, and they can fly, they were 747s or whatever they were. They can fly them on one engine, and they eventually got all of the engines going, but one of them was particularly rough. So they flew back to Jakarta. They said they still had no idea what had happened, but when the people came in to clean the plane, they found a lot of little bits of gritty stuff. And then they suddenly realised that it was coming from a volcanic eruption. I mean, it went all around the world. There's such a close... And the captain was Captain Moody, and there was a New Zealand woman on the plane. And she wrote up a story about what went on, and she went and interviewed as many people as she could as how they were feeling right through that. But the long and the short of it was that she wanted some pictures of what was going on the ground, and she heard I'd been there. Yeah, well, it was interesting with Galunggung. This was a little bit about volcanology and all that sort of stuff. Well, the first one is, are you all quite clear of the difference between lava and laha? Are you quite clear of the difference between laha and lava? Neither are any of the newspapers in Indonesia or on the world. Lava is molten rock. And you basically get that type of eruption from basaltic eruptions when you have these molten streams coming down. Well, that is lava. Most of your andesitic eruptions, they dump stuff on the slopes, and Galunggung erupted, I think it started in about March, and it was right through the dry season. It kept erupting and erupting and erupting right through the dry season. So it piled up lots of material all on the slopes of the mountain. And the people from the public works or wherever, they were pretty good. They did a very good job of knowing what would happen. They knew that when the rain came, they would have streams of laha. The water goes into this stuff, and it's very loose. It's all very loose. And eventually it slips, and then it just flows down like a stream of mixed sand and boulders and all those sort of things. So that's laha. And the lahas from the volcanoes around Bogor or south of Bogor, they reached almost to Jakarta, but not quite. But they weren't lava, they were laha flows. And from Garut, you look at one of the mountains down there, and it's got lava flows. You can see the lava flows are winding their way down it. If you go to Garut, you can have a look and see. Yeah, let's move on to that. Oh, look at, there you are. That's just showing off my Indonesian and my Spanish, you see, because I go to Santiago to teach. And the reason, and I have to be very grateful to Indonesia for this, that I got invited to Santiago in Chile, because on the Andes, now this is an interesting thing too. How shall I? The word andesite came from the Andes because a geologist many years ago was doing a geology of the Andes down there, and he came across every so often there's a volcanic eruption because you've got a fault line there. You see when you've got all the stuff being up first and things like that. And the University of Chile, some contractors came to them and said they were having problems compacting this funny soil down the south of Santiago. So the university got it from some students. Students are very useful for university staff. They can do all their work for them. So they got them to do a survey, a literature survey, and they came across my papers, and so they worked out that that must surely be the same soil. So that was why they first invited me over there to talk to their students and their staff about these particular soils just for 1 week, and that was what I did. And we travelled south at one time to have a look at this, and then shortly after that, they invited me to come over and be a guest speaker at their annual soil mechanics conference. So I went over and did that. And then after that one, the lead professor that I was working with, Professor Verdugo, Raman Verdugo, he said, if we could find enough money to pay your accommodation and your airfare, would I be prepared to come there for 1 semester, which would be about 3.5 months? And I thought about it, and I was very keen to do it, but I had family obligations and things like that, but I talked it out through, and I said, I said to one, I'll come as a trial, and then if it works all right, I would come back every second year. Otherwise, it was too much time away from home. So I did that. I had to spend a lot of time putting the course together. So if I hadn't come to Indonesia, I would never have got my invitation to Santiago. So Indonesia is very important in my life, and you don't realise how important it is because this present trip that I am making was supposed to be in 2020, just before COVID came along. I better try and save my voice a bit. Thank you very much. Where did I get up to? Yeah, I went there. Yeah, talking about this trip, it was had all our flights paid for, I think, and we were all ready to come when COVID came along, and we had to cancel it all. And then other things have come and gone, and some of my family, not Richard, some of my family thought I was getting too old to be travelling back to Indonesia. But eventually, Judith is not here. Judith was quite reconciled to it when I put it to her that I would only come to Bandung, to Jakarta and Bandung, and then go home again. And my wife wasn't very keen on Jakarta. She thought it was too hot, too dusty, and too much time sitting in traffic queues and things like that. And when I asked my daughter, Kay, she's got a mild intellectual disability, but I asked her what she would really like to see in Indonesia if we went back. She said Bali Bird Park. There was a wonderful bird park in Bali. It's absolutely fabulous. And Borobudur. So later in the year with my wife and my other daughter, and probably with Judith, because Judith sort of organises everything for us. We're going to go to Bali for a few nights and then Yogyakarta for a few nights. What other things can I tell you of interest? Oh, it must surely be time for questions now. Dan saya masih bisa bicara bahasa Indonesia, jadi kalau mau pakai bahasa Indonesia, coba saja. Ada saya kira saya bisa bahasa Indonesia. Now, let's try one more. Is there another slide? No. I think I was going to put up a slide. How to become a better geotechnical engineer. Probably number one is spend less time in front of a computer, I think. And number two is really, in order to judge whether your field data or your laboratory data is reliable, you need to make yourself very familiar with field testing and laboratory testing. I almost think a good geotechnical engineer should know how to do all of the laboratory tests themselves. I could do them for myself, but that's partly because I spend so much time teaching other people how to do them. And to have a look at things, look at cuttings. Every time you see a cutting, have a look at it see if you can tell what sort of geology it is and things like that. There are various additional measures that people are making with CPT tests. They are putting some sort of a piezometer into the point so that they're measuring the pore pressure, static or at large. And I was at a conference once when they were showing graphs coming from the piezometer thing, and it had a funny aberration every 1 meter. It showed a very surprising layer every 1 meter. And I didn't say it, but I thought it. You always change your rods every 1 meter. So that means the ones in the ground are sitting idle for a little while and gives it time for the pore pressure to change. So somebody else stood up and said, I'm sure that's not the layer of soil, it's just how long the water there has got to change while you put the next, because they see, the modern equipment for doing CPT tests is a big vehicle, heavy enough so you don't have to have any weights, and with all sorts of sophisticated stuff that will which will calculate and process your material as it comes through, and then it'll plot all the graphs off too in the vehicle for you to have when you. Now, what was the other thing I'm going to say? Yeah, in order to, well, in one of our city administrations, or the city council in New Zealand, in order for people to get permits to build on slopes or anything slopes, must show that the slope has a safety factor of 1.5, I think, for normal conditions, and 1.2 for earthquake or something. Well, what is mostly happening, well, I think it was entirely happening, there are quite a number of consultants. This is a place called Tauranga. There are quite a number of consultants. And they're producing safety factors, all right, but they're, the parameters are just guessed. They're not doing any laboratory tests. So it is very easy. The New Zealand Geotechnical Society strongly opposes this, and I think any geotechnicalist should oppose the idea that you should put a safety factor on a particular slope. The most useful piece of information when you're assessing the stability of a natural slope is the information you get by walking over it, and walking over it here and walking it over there, checking in the area whether there are any cuttings of that similar material. All those sorts of things are far more important than particular items of data. I mean, certainly you may like to do boreholes to have a look at the material, or particularly dig holes to look at the material. But the idea that you can use slip circle analysis for natural slopes it's a lot more feasible in the northern hemisphere, where they've got a lot of sedimentary clays, and they're very uniform in their properties. Whereas in residual soils, for example, where you've got a residual soil, your water table is very likely to fluctuate with season. In other words, it will rise in the wet season and it will dry out in the dry season. In London, the water table is never altered by natural things. If somebody does an excavation or something, it will move. So at least in clays like London clay and some of those other clays they are very uniform, I must say. And you haven't got an issue with the water table, so you could do analytical analysis. I got out a couple of books to have a look at what they said, one by two of America's leading books. And they both said that applying analytical methods to natural slopes is very difficult because of the uncertainty of the measurement of your soil parameters, the uncertainty of the seepage conditions and things like that. Two of them gave a very good assessment like that. But one of them was quite different and said something like geotechnical engineers have now developed the science to a stage where they can apply analytical methods to natural slopes. So it was opposing the other two, and it was wrong. That particularly in residual soils, you've got the problem of measuring the parameters and the difficulty of knowing what water table to assume in your analysis. There's, I think there's an area somewhere near Surabaya where they've got big problems with shrinkage and swelling soils. And they are definitely sedimentary soils. They're the ones that plot above the A line, those ones down near Surabaya. And I had some photos from somebody, from my friend Mark Dobie, and he had pictures of a very gentle slope with a paved road of some sort at the top. It was a very gentle slope, but it was already slipping, and part of the road was already starting to slip, because that would have been montmorillonite clay for sure, very active, very weak, very susceptible to shrinkage and swelling, all those sorts of things. And it's the same in Santiago. Santiago itself is on a very firm type of material. Not a hard material, but a firm material. But there's another area some distance, some kilometres out of Santiago, where they've got problems with shrinkage or swelling. Now is question time. Jangan malu.
Yeah, okay. This very insightful and interesting presentation from Professor Wesley. Yeah, many of his experience has been, he has been involved in many geotechnical experience even since I was even born. So I learned a lot from him. And we also just learned that Professor Wesley is actually an Australian secret agent. Like that. Okay.
Can I just make one comment? When I gave a lecture, when I used to be a lecturer, and I asked for questions and nobody asked a question, I always said, well, it's one of two things. You have either understood all of the lecture, or you have hardly understood any of it, but you are too malo to ask a question.
Yeah. Okay. We also like to say hi to the hundreds of online participants in YouTube channel. These are the camera. Say hi, and thank you for coming for this session. Maybe we can move to the question and answer. Is there any question from the audience here? Anyone? the gentleman over there.
Thank you. There is a question for you regarding about the Galunggung, Mount Galunggung eruptions. There's interesting things I want to ask to you. How significant is the impact of the Galunggung on the site? And also, and what being done with the residuals from the eruptions? Because as you know, the eruptions always give the residual material on the site, and what did you do for that residual?
My hearing is not so good. I better come and listen more carefully.
Okay, I will repeat my questions.
Sure.
How significant is the impact of Galunggung eruption to the site?
The effect of erosion.
Impact of the eruption. Galunggung eruption, Mount Galunggung eruption in Kamojang site. Yeah. It's about 1982.
Oh, of Galunggung.
And also about the residual materials that came from the eruptions. How did you do about that?
The eruption destroyed when the Laha flows started. The government had built some barriers using what they call what are those where they have gabion basket. You know gabions? You have a basket made of wire and you fill it up with rocks and stones and then you put the lid on it. So they had built quite a few using gabions, and they had also built clay embankments. Some verse they had clay embankments, and they were pretty successful, but there were some small villages where they couldn't control the Laha. Because I was involved with the geothermal things, I went back after the rain came. You see that everybody knew when the rain came they would have lahars for sure. And there was a picture of one house where it was almost full of laha. It came in through the door and the windows and filled it up. But I felt that their control was pretty good. And Galunggung was a bit special because its crater was rather like a horseshoe. In other words, right around in one place, the crater was still intact, but in one place it had been eroded or something like that. So they knew pretty well where the laha would come from. They managed to control it. Yeah. In one place where the gabion wall was probably almost as high as this, and the laha flow has deposited material all the way down, but not quite high enough to go over the top of it. And I don't know whether I think it was part of the Public Works Department that had the unit to do this, but I think Indonesia probably, like with a lot of other countries, now has special units for handling eruptions or things like that. That's about all I can say. Thank you.
Okay, thank you.
Thank you, Pak Irsan. Ya. Any other question? Okay, Pak Antoni. Pak Antoni is a lecturer from the Bina Nusantara University.
Hi, Dr. Wesley. I'm Anthony. I'm a lecturer in BINUS, I believe you came several years ago to Venus. I want to ask about the red clay. I done some tests recently on the red clay. I prepared the soil by oven drying, but when I did the grain size distribution, it actually 50% of it is considered sand particles. I'm wondering whether we should grind them using some materials first before we do the hydrometer.
You just say that again. I didn't quite catch all of it.
All right. So basically, I oven dry my red clay sample. After that, I did the grain size distribution, but it came out classified as sand. Yeah.
Because you were hearing better than mine.
Red clay sample was oven dried. Half of it came out as classified as sand. So I took a red clay sample, oven dried it, and half of it came out classified as sand, the grain size.
Yeah, I can't. Yeah, I understand what you. Where did the clay come from? Yeah, I can't explain that. It doesn't say. In my opinion, if I had red clay from anywhere in the Jakarta area and I put it in the oven, it would come out almost rock hard. As hard as rock, almost. Yeah. But again, I don't know how pure red clay is, but generally it's pretty pure, yeah. So that's about all I can say.
Yeah, thank you, Pak Anthony. Any other questions?
Well, one point I would make, if you want to know whether your material has got elephane in it, do your Atterberg limits in its natural state and then put it in the oven. And then see if you can still do that. I mean, if it's a high elephane content and you put it in the oven, it will come out as a very fine sand. And you can't make it go back to a clay because it changes the composition. So if you really want to have some indication of whether it's got elephane in it, that is by far the simplest. Getting hold of somebody who will do a proper study of it costs a lot of money. You have to go to somebody who's got the money. The paper that I originally published in Geotechnique in 1970, whatever it was just a piece of good luck that a friend of mine who was a geologist, in fact I lived, but he was visiting Indonesia for some other reason, and he took an interest in what I was doing. And he said if I could get some samples to him of both the red clays and the other ones, he would get his staff to analyse it and give me a report on the proportions of whatever middle. So that was in 1972. At that time, they didn't, that pretty picture I showed you of the mineralogy of the form of the halloysite and the form of the elephane, that wasn't available. The Japanese only had the ability to do that about 20 years ago, probably. I went to a conference in Japan, and the unit that did a lot of investigation into elephane was fairly close by, so I went there and spoke to the guy, and the same had happened there as in New Zealand. But we used to do a bit of research into elephanes, but the money for that had dried up. And the same in Japan. He said, we're not doing any more research into elephane clays because the government won't give them the money to do it. So that's where it. But he gave me one of their photographic plates of some sort, which showed you all the the very tiny spheres and the threads going in and around it. So that paper that I published on allophane and halloysite and related it to the mineralogy, there hasn't been another paper on that that's showed any analysis of what the clay minerals actually were.
Yeah, thank you. Any question? There is a question from an online participant.
Good.
From YouTube.
Oke, Prof. Wesley.
Okay, this is maybe a principal questions. The participant asked if we want to do slope stability analysis for long period of time.
For what?
Long period of time.
Oh yeah.
Yeah. Should I use drained or undrained condition? That is a very basic questions, I think, but everybody still cannot decide about that.
Most definitely, it must be a effective stress analysis. You couldn't possibly use undrained strength to estimate the long-term stability. I mean, in theory, I mean, you might be. Now, the short answer is, if are we talking about a natural slope or a cut slope? If you were to use undrained strength on a natural slope, you'll get a grossly optimistic.
Well, he didn't mention anything, but maybe it's in general. Maybe in general. Yeah, he did not ask in specific about the man-made slopes or maybe a natural slopes, but maybe he is talking about in general.
Yeah. I mean, there's a place for an undrained strength. There's no doubt whatever about that. I mean, if you're building a building on a clay, I think most people would certainly use the undrained strength because it's easy to measure and it's safe. Whenever you build a building on clay, it will cause consolidation and the strength will increase. So for designing foundations, it's much simpler to use the undrained strength, without any doubt at all, yeah. But for long-term, if you're doing an excavation, for example, if you're doing an excavation, that is the opposite effect. You're taking load off the soil and water is going to start to seep towards the excavation and the strength will go down. So in that case, I mean, you might be able to guess what the undrained strength would be, but you can't do anything else other than an effective stress analysis if you're determining the long term. Yeah, so in the case of a foundation load, your situation is that the safety gets better as time goes by because water gets squeezed out of the soil. But the other way around, where you dig a hole, gets softer with time as water seeps towards the hole. There's a picture of that in my book. Let me just see if I can find it. Thank you. I'll just have a rest for a minute while I examine this. Look. Yeah, this picture here. That one. That one there. That's what I just was saying. Yeah. That's consolidating the soil, isn't it? Squeezing the water out of it. When you dig one like this, the water flows towards it. Yeah.
So maybe you can, the cameraman can show the. So this picture explain about the difference when you show do the undrained or the drain analysis. Yeah, I hope this make clear about the questions from the participant. Okay, thank you, Mr. Wesley. There is another question. There is another question from Mr. Billy Tanadi. Yeah. He is asking the question about, is there any significant difference on field test correlation between the sedimentary and residual soil? Is there any difference on field test correlation between sedimentary and residual soils? That's the question.
All I can say is that most of the correlations that exist, particularly between cone penetrometer tests, they have all been based on sedimentary soils. So there probably is some difference, but I would like to be sure about that. But most correlations, well, particularly with CPT tests, the correlations are almost all done on sedimentary materials. I suppose the big difference is that it's only with sedimentary soils that you generally get a uniform material, whereas with residual soil, you see the process by which sedimentary soils are created, you have erosion, and then you have transport, and then you have sedimentation. That process is a sorting process. It sorts out sands from clays and things like that. So you tend to get nice, uniform, tidy materials, but you'll only rarely will you get it with, well, I suppose the red clay is one example. That the red clay is generally fairly uniform, whereas, and again, that's been formed by intense weather and seems to convert. I mean, if you have weathering on a laha, you'll eventually end up with red clay. And here in Jakarta, I'm just trying to think of where the red clay is exposed. But the red clay here, at least the top, I don't know, 4 or 5 meters is probably very uniform. But I suppose that's a little bit of an exception, because most residuals, some of our residual soils, residual soils in New Zealand are reasonably uniform, but not very uniform like sedimentary materials. So there is a difference.
Yeah, okay. I hope this can answer the questions. Is there another questions from participants here? Yeah, maybe if you want also to deliver the questions in Bahasa Indonesia, I will try to translate it to for Pak Wesley. Oh, okay, Pak Andrianto. Pak Andrianto is a tester company.
Hello. Good morning, Professor Wesley. Mike, you have touched it a little bit earlier. What is the difference between residual and sedimentary soils in the application of our calculations? That's the first question. Second question is a bit naughty, yeah, maybe. Why in geotech engineering, why are we putting soils in boxes? Your clay, your sand, your sedimentary soil, your residual soil, effective stress, total stress. Why is there no unifying theory? Maybe just naughty question. I have this question since I was a student. Maybe just 2 questions.
Let me just think what I should say. You don't need to know for certain whether a soil is sedimentary or residual. But what you do need to know is you must not apply concepts derived from sedimentary soils to residual soils. Particularly the obvious one is the use of the log plot when you are plotting the results of odometer tests. It got sort of established very early in the days of soil mechanics that you should use the log plot, but using the log plot, well, one of the professors in Norway, Janbu, for years he has been telling the organisation they should get rid of the log plot, because half the time they use the log plot and they have a curve which goes along, and then it goes over, and then it comes straight down here, and they draw this line on this, and they calculate a compression index or something. Often in those situations, that is obviously total nonsense, because if you come back up along here, the compressibility of the soil is very different. That parameter has got no relationship to calculating anything really. But people didn't. I went to a seminar in Italy, and I showed a whole lot of graphs showing that the use of the log plot was very problematic, and they told me I should go and talk to Professor Janbu, because he has been telling the profession that for years. So things like pre-consolidation pressures can't possibly have any meaning on the residual soil, because there has not been a consolidation process. It's been formed just by the chemical weathering on a rock to a clay, but there hasn't been you can have a yield stress, but you cannot have a pre-consolidation pressure. And I think in Imperial College, they say they are mostly using yield pressure rather than pre-consolidation pressure, because yield pressure to you is safe. You're going to have a yield pressure on any soil, but you're not going to have a pre-consolidation pressure. I mean, you might like to call it that, but it's got nothing to do with pre-consolidation if it's in a residual soil. Does that answer part of your question? Yeah, the important thing is not to assume that your soil is sedimentary so that you can use the logs. My view is only for very soft clays, like all along the coast of Java, those very soft clays, they're probably 20 or 30 metres deep or so. Oh, many of those are in Malaysia too. In that situation, you've got a normally consolidated clay, pretty uniform. In those situations, the use of the log plot would be quite justified. But if you've got a very hard sedimentary soil, I still don't. I think it's better to go with a linear plot. But it's very hard to persuade people. I think I'm right in saying that the Americans in particular only know the log parameters, whereas a lot of the British people use the EMB one, the linear parameter, for doing their settlement estimates. I was going to say something. Oh yeah, one of the a rather nice guy, Das, V-A-S. He writes textbooks which are widely used in America. And I was communicating. He was asking me something, and I was bringing up with him the use of the log plot. And he was working on a new version of his book, and he said he would send me a copy when he got it completed, but I haven't heard from him. But he did acknowledge that it was time that the Americans started to look at their use of the log scale, because it was really totally out of place in many situations.
Yeah, thank you very much for the explanation. Maybe if you don't mind, we have one last question. Okay. This is the question from online participant, Pak Jody Hapsoro. Pak Jody Hapsoro, he wants to ask about what is the difference in your experience in Indonesia, in your home country in New Zealand? What is the difference in geotechnical aspects?
Yeah, good question, but I think there's a cultural difference. And I have to choose my words carefully. When I worked at the institute where I was, it was very difficult to get an engineer to go into the laboratory. It's a cultural thing that the laboratory is the place for technicians. And it came up too, when I was doing the courses, the ones who came from Java were very reluctant to go into the laboratory, whereas people from the outer islands would go into the laboratory. So that same issue is an issue in Malaysia and in India too, that the laboratory is where the technicians are, not where the engineers are. That's what I would say is we don't have that issue at all in New Zealand. I mean, a person is not rated whether he's got status somewhere or status somewhere else. And there are other things, of course. When you do cone penetrometer tests here, Are you still doing it the old way? Mechanically, I mean? Are you still using the mechanical apparatus?
Yeah. Yes. That is exactly we still do here.
Good. And I think that's right. If I see a person doing a CPT test, if I go to the field to see whether somebody is doing a CPT test correctly, I know immediately, I can see what is happening. But if they have a sophisticated set of instruments that need to be calibrated or all sorts of other things, there's no way I can tell whether the results are reliable or not, because I don't know the calibrations or how often they do the calibrations. I think the continued use of the mechanical one is ideal for Indonesia. Otherwise, you've got the problem of making sure your instruments are calibrated. And I don't know, do any of you know Mike Doby? He's the person in charge of the Tensar company. He's done some work in Malaysia showing that the temperature can be quite a very influence on your calibrations. So the calibrating your load cells and all those things is not all that simple. So on that basis, I think the continued use of the mechanical one in Indonesia is ideal. It can be made here. The only part you have to introduce are the Bourdon gauges. And the institute, when I was at in Bandung, they made they followed what the Dutch had done. They made their frames and things for SBT tests in the Bengkel there.
Yeah, actually that is a bit relief for us in Indonesia. Maybe because when you first come to Indonesia, you introduce the CPT, the mechanical CPT ones. And today, we are still using the mechanical CPT ones. So that's actually one question from me. What is your advice about the use of mechanical CPT? So should we still use the old way to use the mechanical CPT, or should we move into the maybe more advanced technology like a CPTU or something like that?
No, I would stay with the mechanical device.
Okay.
As I said, I can go on a site just to check how they're doing their tests and know whether they are reliable or not. And one time, this was on one of the geothermal projects, a company had arrived when they were doing their test, and I was watching them doing the test. And it was with the biconus, with the friction sleeve. They were taking their one with the to measure the cone resistance, and then on the next one, they were just sort of touching it. It should be going once it hooks whatever you call the sheath into it. It should be pushed 4 centimeters, and they were just touching it and recording it. And I told them they had to do it and showed them how to do it. You make sure you get a reading, and then you push it gently for another 4 centimeters and take another reading. And they were just touching it at the top. Do they call it the biconus? What do they call the one that has the friction sleeve behind it? That friction sleeve was developed in Indonesia because when they first, this is just a bit of history, when they first developed the CPT tests in Holland, they were developing it in order to estimate the bearing capacity of piles, because most of the surface stuff was pretty soft. And then you had a very hard layer, so almost all of your bearing capacity was coming from end bearing, not from friction sleeve. But when Begerman realized in Indonesia, particularly down on the coastline, there was no way they could possibly use point bearing piles because they would be going down 30 meters or 40 meters in some case. So he sought to devise an advancement of it that would measure the skin friction. That's why he invented that. He found out that if he used uniform diameter casings, that the resistance would go up down to somewhere about 8 or 10 metres. Then it wouldn't go any further. So pushing it down further wasn't getting you any measure of the skin friction at all. So that's why he worked to develop his device, so that now you push it down for 4 centimetres, and then it hooks onto the friction sleeve and it pushes the two down together, and then you process the results. But when I first wrote Mechanic HATTI, there's a formula in it for calculating the bearing capacity, and for end bearing the safety factor was 3, and for skin resistance, friction resistance, the safety factor was 5. And somebody called it my formula. I said, well, it wasn't my formula, it was what the Dutch were using. And the Dutch were right, that the measuring the skin friction is a lot less reliable, than measuring the point resistance. Yeah. So if I was doing it, I would still be using that same formula. But they processed it, so you had a measure of the skin resistance on 1 centimetre of the circumference of the thing there, and then it made it very easy for you to apply it to piles if the piles had a certain diameter as well. Yeah, when I joined that PVT in Bandung, my boss showed me this thesis written in Dutch, and it was Begerman's thesis that he used in order to get his doctorate degree. It was a study of the CPT test and the extent to which you could measure the skin resistance of the piles. My boss gave it to me, and he said he would, if I was really interested, he could translate the Dutch into the English, but I left it at that, actually.
Yeah, okay. Thank you for your explanation, Pak Wesley. Well, actually, there are many questions here, but due to our limitations, time limitations, we should end this discussion. Yeah. And let us give a big and round applause to Pak Wesley. Congratulations. Now I would like to invite Pak Ali Iskandar. Pak Ali Iskandar is Vice Secretary of the HATTI, yeah, or the ISGE, to present the Pak Wesley the token of appreciation from ISGE, Indonesian Society for Geotechnical Engineering.
Thank you very much. Thank you. Thank you all for coming. Thank you for your attention.
And also there is a souvenir from our host, Geotech Efathama. Yeah. Ibu Emi would like to present the small souvenirs for you. So maybe this can...
Thank you very much. Thank you very much. Thank you.
And Bu Emi, please stay on the stage because there is appreciation from HATTI to Geotech Efathama because of the participation as becoming the host today. Okay, I would like to say thank you Oh, okay, okay. Let's take a picture.
Oh, ada sempurna ini. You can hold this. Thank you.
Okay, we would like to once again say thank you to Professor Wesley for coming to here, for coming to Indonesia, and also would like to thank you all the participants who is coming here, and also for the online participants enjoying the show from the YouTube channel. And we would like to say sorry for any maybe mistakes or something that is not yang tidak berkenan begitu ya. Okay, let's give us a big and round applause for us. Thank you very much.
Great. Drop that into my bag, so that'll go away. That's great.